Okay, let's go to the material. Okay, now here's where I got stuck yesterday, Tuesday, and I appreciate the fact that I think everybody waited for me. Boy, I was crawling underneath the table here, pulling the plugs, waiting for the machine to reboot itself. Then it wanted to do an update, didn't let me have a chance to say no because I couldn't get up from under the table fast enough. So we waited longer than we absolutely should. And this should not happen anyway. But let's see if we can get right to the material. Looks like it's going to happen today. There we go. Okay, you're here with me at week 2. Okay, Charlie's web page has been moved down. One reason that you may want that page, lots of reasons. But if you look over here under laboratory material and you look at the bones skeletal system, you have the skull, vertebral column, upper and lower are appendicular skeleton. And then you have the knee. And you also have x-rays for a little bit later on. You can open any of these or all of these and get just plain lists with no decorations and lists of material that is to be covered. These are all fair game for practicum 1. Okay. They look pretty much the same. The format's definitely the same. Okay. So you can get your list right here in a nice clean fashion if you want to look at them or care to print them. Okay. Same thing will happen in the second unit, the third, and the fourth unit, which is farther down the page. These links, you always have to click a second link inside of it to open up the web page. It's not an error page. It's just directing you elsewhere. Okay. The week 2 assignment is chapter 6, I believe. Okay. No, I'm sorry. This is chapter 9. It's going to be 169 and 2. I said that before. Okay, 169 and 2. I sent you an email either about this or something else. I sent you an email yesterday. If you check through your mail because you didn't see it, you find it, great. If you check through your mail because you didn't receive it and you don't find it, you need to send me your email again. Be sure you're on my list, okay? You got an email yesterday, Wednesday, the 26th. Okay. We did the organization of the levels of organization, and on the 25th we did cell structure. We looked at some new bones of the ribs and the vertebral column. Okay, I inserted this link here for you. It's a very good link by that same author. Here's our recording. And here's all we have to do today. Cellular processes. Anything's a process so long as one thing follows another. Good process and application or whatever. But in biology, what we're looking for in processes is chemical changes that keep occurring one after another to accomplish some goal. That goal could be to manufacture material that can be used in respiration, or it's the result of respiration. So the cell can continue to form its structures, and to replicate. When we look at cellular processes, we often involve the movement of water and of salts. Water is the universal solvent. Everything is dissolved in water and mostly made up of water. And salts. Salts don't mean necessarily table salt, sodium chloride, or anything like that. All the minerals that are available for a cell to take up and utilize in constructing or reconstructing itself. Cellular processes are divided into two groups, passive processes, and when we get to it a little bit later, active processes. A passive process is one that does not require work by the cell or the organism in which these processes occur. Well, I think you and I, in our experience, find that nothing goes on for free. There's always some energy expended somewhere, okay? And that energy we call work. But in passive processes, we consider that there is no additional energy going to be spent. If there is energy spent at all, it was energy that was provided to the cell, either through Brownian motion, just a random motion of molecules and atoms, okay, or something else. But the cell does not have to expend any of its own energy to get a passive process to work. Okay, now a couple that will seem rather infantile almost to you, I hope. The first passive process is diffusion. We all have real life examples of diffusion. Okay, for instance, if I were to take a jar or a container of perfume, and there's none of that perfume in the room except in the jar. And then I open the jar, we expect the molecules to begin to evaporate and concentrate first around the jar, but then to diffuse out until they become actually totally diffuse and equal throughout the room. How long do you think it would take a jar of perfume, small 1 ounce jar, opened to diffuse throughout the room equally, so long as I got the window shut, the room is sealed up? A minute? 2 minutes?
Half a minute.
Half a minute, thank you. Okay. I think it'll take longer. I think it'll take days. I think it frankly would take days until all the perfume actually had vaporized, and all that's left in the perfume bottle itself is perfume vapor equal to the concentration in the room itself. Yeah. What's another word that you could give me? Just one word that takes the place of diffusion. Not many people get this one, but it's not hard. It's probably half of you are thinking of it and afraid to tell me. Don't be afraid to be wrong. Better to be wrong here than on the test.
Is it dissolving?
That's good, but that's not the one I was thinking of, but that's good.
Is it dispersal?
That's the one I wanted. Dispersion, okay? Now dissolving is good, okay? Dispersion is the one I was thinking of too. And so obviously so are you, okay? There's a simple diffusion diagram at the bottom of the page. Okay. And it uses one of my examples, but it uses beakers. I like to think of a fish tank. Think of a fish tank. Make it a rectangular fish tank so they're both thinking the same way. And there's no fish in it, there's just water. And now you take some colored vegetable dye. I like blue. And take an eyedropper and put some blue dye in one corner. Will that blue dye spread throughout the fish tank immediately? Of course not. It takes time. Will it spread or diffuse or disperse through the fish tank eventually? The answer to that one is yes, it will. And it will continue to disperse or diffuse until equilibrium is reached. Equilibrium is when the concentration of solid and solvent are the same throughout. In the example at the bottom of the page, where it says simple diffusion and has 3 beakers, they start with the beaker of water and drop some dye into it. Now, immediately the concentration of water is higher where the water was, but the concentration of the dye is higher where it was dropped in. Higher concentration moves to lower concentration, so the dye spreads out. Higher concentration leads to lower concentration, so the water moves in. They're both going to be moving, not just the solvent, but the solid as well, until they reach the 3rd beaker, where it's trying to show you that an equilibrium has been reached. There's an equal amount of water and dye spread throughout. This is a simple process that happens in all of your cells, all parts of your body. Requires no work. When I was in science class, my first science class was in 8th grade, I suddenly got a wake-up call. My God, this is hard. Wasn't, if I look back on it, but and I enjoyed it a lot. But we hit the word osmosis as a passive process, and boy, that's where everybody fell apart. Osmosis may have given you trouble as well, but it shouldn't have. Osmosis is just a special type of diffusion. It's diffusion from an area of higher concentration to lower concentration still. But the molecules that are going from higher concentration to lower concentration pass through a membrane. That's all. They pass through a membrane. Picture, 500 people on one side of a doorway at the airport, probably. And there's only one doorway or one security check, and they put you through one at a time. Okay, you're still diffusing from the crowded area to the less crowded side, but you're going through a membrane, in this case, the security check. The most common membrane that we can think of course, is the cell membrane, the plasma lemma. And so we have water being able to go from where it's more concentrated to the side of the plasma lemma where it's less concentrated. We have solids often able to go from the side of most concentration to the side of lesser concentration. I said, usually. Solids sometimes are excluded. The cell itself says, no way, you're not coming in. It's almost like the cell is a bouncer, and selection chooses who gets to come in. But when they do get to come in, they'll usually come in through a type of diffusion. But since you cross a membrane going from outside to inside, the term osmosis must apply. Let's see the primary part here. The cell membrane or plasma lemma, primary semi-permeable membrane. Okay. Where did I get that word semi-permeable? Right from this definition. Osmosis is the diffusion through a semi-permeable membrane with some things being allowed to cross and others being prohibited. The word semi-permeable means some things get across, maybe most things get across, but some things do not get across. Picture for me, if you would, a room with a table and a chair and 2 jars. And you go in, you're closed in. There is a window with hinged shutters. It has a window screen, and the screen is intact. You have 2 jars on the table in front of you. One is filled with flies. Okay. The windows are closed, the screens are intact, the door is closed. You let the flies out. Shake them out if you have to. I know that's not passive, but we'll speed this along. What are the flies going to do? Yeah, they're going to annoy you. They're going to be all over the place. Oh, some of them may hide up in the corner for a while, but their place will be taken by other ones. And they spread out through the room. Can they get out of the room? And the answer is no, because we've got the room sealed up. Okay. Now, open the second jar. This jar is filled with that perfume we had, and it's got a big mouth in the jar, so the perfume evaporates rapidly. Can the perfume get out of the room? Again, no, because you've got the room sealed up. Okay. Go over to the window and pull the 2 shutters or closures open. Now can the flies get out? Remember, there's still a window screen. No, they can't get out. But can the perfume vapor get out? Yes, it can go through the window screen. So here we have a membrane, the wall of the room, that's semi-permeable. Some things can get in or across it, and other things cannot. We have that situation in our own bodies all of the time being faced, but the best example is always to look at the circulatory system. I'm going to start with the center of the 3 diagrams, where the red blood cells floating in the plasma is shown as black. Okay. The cells look to be normal in size. They look like properly shaped red blood cells. And the concentration of solids inside and outside is the same. The concentration of water inside and outside is the same. Which should we be talking about? The concentration of solids or the concentration of water? Doesn't make a bit of difference. If one is high, the other is low. If they're equal, they're equal. When these terms that I'm going to show you, these 3 across the top, were first developed, people were looking at the strength of the solid, okay, and the strength of the solid inside and outside here in these properly formed red blood cells is equal, as is the strength of the water. And so we call this situation iso, meaning the same, tonic, the same strength. Okay, that's the easy one, I hope to understand. That's the way most of the things going around in your blood are. We also have the situation though called hypertonic. In a hypertonic situation, the red blood cells are surrounded by a higher strength of solids. A higher strength of solids. What happens when the solid concentration, for some reason, I'll give you a reason in a moment, is higher on the outside? Water is going to head for it to dilute it down. Water moves fast, faster than any solid. And the water leaves the red blood cells going into the high tonicity area of the plasma. But in doing so, the red blood cells are squished. Okay? They're not going to function properly. The red blood cells in this situation are crenated. Crenation means that the red blood cells are deflated. Now, given enough time, eventually, and should these cells survive, the water will begin to come back in as the solids come in. The solids will try to get in. They're in a higher concentration outside. As the solids come in, the water will come in. Wherever the minerals go, the water will follow. That's a kind of important statement. And then it would revert back to this, the isotonic situation. But water moves rapidly. And if it has an unequal distribution of solids and solvent, the solvent moves right into the solids. And we have a little bit of a disaster on our hands here. You can get this sort of a situation when you try to get rid of varicose veins. I'm going to assume that everybody here knows what a varicose vein might look like, at least have heard of it, to maybe even check themselves to see if they've got any. You can inject salt water, that's solids, heavy solids, into the vein. That will cause the red blood cells to collapse. That in turn, with a high concentration of the salt solution, will cause the vein to collapse. And the varicose vein literally disappears before your eyes. It's dead, it can't come back. And don't go in and take all my varicose veins out at once. Yeah, you'll have very poor circulation if you do that. You got to take them out gradually. The other situation is where you have a high concentration of solutes inside of the red blood cell and a high concentration of the solvent outside. The solvent outside will rush in. Remember, the water is the solvent, can rush into the red blood cells quickly. And that can cause them to expand or even explode. This is a hypotonic solution. Hypotonic, where does the word come from? It comes from the plasma having less hypo strength of solid. In other words, more water. In the last 10 years, the emphasis has moved from talking about the tonicity referring to the solid to referring to the water instead. That's confused a few of us for a while till we caught on. Most of the people who are hearing it for the first time, they don't get confused because they were never told otherwise. Okay? But it's the water that will move first. Always. It's fast. And the water always goes towards the minerals. If these red blood cells explode, which is likely, it's called hemolysis. Hemolysis. Now, I have a description here of each of the three situations. Here's the isotonic situation I described to you in text. Here's the hypotonic situation and the hypertonic situation. Words like hemolysis that I just used are all included in this text. So for us right now, there's nothing new in this text. But when you go to review this page, getting ready for the lecture test, you should read this again. So we've had diffusion and osmosis as passive processes. The third passive process is facilitated diffusion. Sometimes it's called passive transport, but I prefer myself the name facilitated diffusion, and that in bold there means that that's the word I'll use on the examination for you. Okay. When a solid approaches a semi-permeable membrane, like the cell membrane, the plasmalemma, they would try to cross by regular osmosis. However, the cell has embedded proteins in the plasmalemma that act like a slippery slide. And the solids, when they get there, they just rush in. They rush in faster. Here's normal. And here's what's what we call carrier proteins, which pulls them in rapidly. Don't be confused by the fact that there are three over there. They've had more time, and only one over here. Facilitated diffusion is diffusion that takes place faster than we would normally expect it to. Okay. Let me give you a real life example. You get out of the airplane. I don't know where you would go these days, but you've been someplace probably in the past. You get out of the airplane, you squeeze through that front door, your feet are coming back to life, you feel a little bit better. You get out, you move away, you go up that ramp, and then you get to the carousel area or the meeting area, and you spread out from all those people that were crowded with you in the airplane. Okay. Well, that's regular diffusion, going from an area that's crowded to an area that's less crowded. That's not facilitated diffusion yet, but you're walking away from all these other people, maintaining your distance probably too. And then, oh God, thank God, there's a speed ramp. You all see these elevator ramps, but they're level. They speed you along. You can walk them if you want to, or you just stand still and let them take you. That's facilitated diffusion. That ramp is going to go whether you're there or not. So you're getting on top of the ramp does not add energy to it. Okay. And it'll take you. It speeds up your diffusion. Remember back to the fish tank that we looked at in the example of diffusion. Had an empty fish tank except for water. We put dye in. Let's put the dye back in at the corner, keep it there. And now add one thing, a goldfish. That goldfish is not going to hold still. It's It's going to swim around the tank, and it's going to speed up the diffusion of the dye. We call that facilitated diffusion because it's being helped along. Okay. Dialysis is the fourth and final passive process. This is the separation of molecules by size. We're really going to beg off here and save the discussion of this until we get to the kidney. I don't think any of you are old enough to have commonly used coin vending machines. Oh, you've used a few, but you put in a series of coins. Maybe you need a quarter and a nickel and a dime. The vending machines when I was a kid only took nickels because that's all anything cost. Well, when you put in all these different types of coins, they've got to be separated from each other. Okay, so you come to a small slit that the coins are traveling down, and the only thing that falls through the slit is a dime. All the rest of the coins continue on, and the nickel falls next, and the quarter falls next, because you keep making the openings bigger. Just because they have different sizes, then we can only accept certain molecules. In kidney dialysis itself, the blood is taken and the plasma is expressed, taken out, and the various molecules that are in the plasma, including uric acid, nitric acid, things that we don't want are separated by size, and things that we do want are allowed to continue. And we mimic the kidney in this so that we remove the crap and we add back the still desirable material. I've heard, but only heard, that people who have dialysis can actually go in and they feel fine, although their blood needs to be cleansed. And they have the procedure done, and they end up feeling crappy for a day or two. Okay. But anyway, dialysis is the separation by size, and we'll come to that in the kidney. Okay, I told you that we would have a second category, and that's active processes. These require the expenditure of energy. I see this sentence doesn't read well. I'm sorry about that. These processes require the expenditure of energy. I'm making a note to myself to correct that. Okay. Energy must be used. Where are you going to get this energy? From the mitochondria, some from the cytoplasm and glycolysis. Okay. Active transport is one type of active process. As organisms that we organize our environment. If you know the laws of thermodynamics, and I barely do, know a couple of them, one of them says that the universe is constantly running downhill energy-wise, and that the lowest form of energy is heat. Okay, and we're constantly running downhill, becoming more and more disorganized. But you look at yourself and the people around you, you're organized. You're not disorganized, okay? You have higher concentrations of so many things in your body then the similar concentrations of the same things exist outside of your body. For instance, you have more iron in your body per square inch, cubic inch, than you're going to find around you in the same volume as you are. Okay, in other words, put an aura around yourself. And in that aura, are you going to find all of this iron? Not unless you're in a barrel of nails. Okay, and we're not going to play exceptions here. Okay, so you have concentrated iron. You have concentrated calcium all your life. Otherwise, you wouldn't have your bones, and you wouldn't be able to regenerate your bones. You have any number of atoms that we could look at, or molecules that we could look at, and show that you have concentrated them. You've even made some DNA. Doesn't float freely in the environment. Now, somebody's going to say COVID or something like that, but that's primarily messenger RNA that's floating free. I don't want to get into that, so maybe I shouldn't have even brought the example up. Okay, you are more concentrated. You are working against the principle of thermodynamics that I was discussing. Well, not forever. When you pass along and I pass along and everybody passing along, we'll give this material back. Okay. I often like to think of myself as a speed bump on the road of life. You know, just everything's nice and level. And here's this bump that's organizing material, but then has to give it up. We are not at equilibrium with our environment. If you were at equilibrium with your environment, you would be dead. We have carrier molecules in the cell membrane. We mentioned this a moment ago when we talked about facilitated diffusion, but these actively pull materials inside. The term actively means energy is needed. Energy is or may be needed to keep the molecules in our cells. Here's the membrane. Here's outside. Here's inside. We have a higher concentration of a selected solute here, or mineral, being pulled inside than is found outside. Osmosis would say that these would just slide back out. Well, so what if they do? They get caught again and they get pulled back in again. If you imagine this as a prison, okay, and if you imagine the concentration of convicted prisoners inside is high, but that the number of prisoners outside may be even higher, but less concentrated, they're spread out. Well, eventually, some of them come to prison or are brought to prison, and then they're pulled in and crowd the inside even more. Active transport, that's what this is, active transport, is the movement from an area of lower concentration to higher concentration at the expense of energy by the cell that's doing the work. Well, somewhere along some movie I saw, it's every prisoner's duty to try to get out. And so some escape, but get recaptured immediately. This is not the only carrier molecule. They're spaced all along the cell membrane. Some of the solutes may get out and get away. Doesn't matter. There's plenty more coming, and we'll repopulate it. We have to pull these minerals in order to utilize them for various projects, such as building DNA. When we build DNA, we've built a large molecule that can't just get outside of the membrane again. It's like building a ship in a bottle. Okay. We can pull the material in, we can assemble it, and then it can't get out at all. The second type of active transport. Okay, here's where I'm getting this active process. Actually, active process, active transport is one, and cytosis is two. We talked about cytosis on Tuesday, and shouldn't need to talk about it again unless you have a question. Cell eating, when a bacteria or cellular debris is brought into a cell, is done by phagocytosis. And cell drinking, when only fluid is brought in with solids, is pinocytosis. Those golf ball like indentations that we talked about, pulling material in, that all requires energy. So that is cytosis, broken into two parts, phagocytosis and pinocytosis. The phagocytosis forms a food vacuole, and the pinocytosis forms a pinocytic vesicle, just to remind you. Okay, any questions? I look down at the counter here. Can you see the counter? Participants, it says at the bottom of your page.
Yes.
Okay, it says 31 right now. And there are 31 in the class, but I count as 32. So there's always one person missing. Anyway, I do take a look at it. Okay, any questions at all? Not difficult? Good. Then let's take a little bit early break and take it till 3:05. That's 11 minutes, if you don't mind. And that'll help the people going into the discussion section later to save a few minutes for them. Okay, I'll see you back at 3:05. Okay. Okay, I guess you can hear me because you moved around. I haven't heard you yet.
We can hear you.
Okay, thank you. Okay, the first question that was asked to me last Tuesday was, had I heard anything about moving back to the classroom or not, what they were going to do? And we talked about that for quite some time. They sent another memo out, and trust me, it has no effect on you whatsoever. But I want to tell you what it is in case you are sent it as well. And you say, well, that's not what we said. Last Tuesday before class, they said that we would go back to the classroom on the 23rd. That's what I told you they said. You know, I'm not vouching for them at all. These things change, of course. But the memo that they finally sent out later in the day, after probably while we were in our session, was that the go back day was the 21st. Now, we don't meet on the 21st anyway. And we don't meet on the 22nd, as I told you, because that's what they call a faculty contractual day. And I never understood those, but they're placed. Their placement is an enigma. I have no idea, but the 22nd is a holiday. So it makes no difference to us. We weren't going to be here the 21st anyway. We're not going to be here the 22nd. And if that's the case, we're not going to be here the 23rd. That's a Wednesday. We're going to have our first lecture test on the 24th. I'm not moving that date at all. A first practicum, I should say, not a lecture test, but the first one is on the 10th. Wait, am I getting this right now? I'm lost track myself. Anybody got this syllabus out or handy?
Yeah, I have it.
Yeah, look for practicum 1.
February 10th for the laboratory. Yeah.
Okay, February 10th. And then the 24th is the lecture test one?
Yes.
Okay, well, February 10th, definitely we're still going to be here. So we're definitely going to take the online version of the test. Okay, and I know I said that on Tuesday. On the 24th, the first lecture examination, it's going to be the same test, no matter whether it's online or if I have to go and take the test printed, run a bunch of a print job, bunch of staples, and bring along a bunch of Scantron answer sheets so we can do it the old way. Either way, it's the same test, so you want to study the same way. Okay, I'm not going to make a firm decision as to whether or not it's going to be online like this, okay, or if it's going to be on paper with all of us sitting down in the laboratory. Okay, questions? That laboratory that we have two actually, but we can only be in one at a time, was built for 28 people, which disappointed a lot of us because we're used to taking classes even up to 50, and which is really too many. 40 would be more likely, but not not the case. They built the laboratories for 28 people. Even with our 31, we're going to have to bring in extra chairs. That's easy. And have extra spacing around the table. But there's no way you could take the number of people we have, space them 5 or 6 feet apart around the room, and not have them go out into the hallway. So they, I know they're considering that too. And oh well, I guess I just want to say something since you're not okay. Okay, let's go back. And that's where we were. Okay, after 127 on our date, the name of the topic we just hit, and the word lecture. For the lecture exam, when we get to that on the 24th, you definitely want to have memorized or know all of the material on anything here like this. It says lecture, 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 lecture. Okay. I often end up indenting for you so that you know exactly what to study. But the word lecture is the giveaway for the lecture test. When it says lab, that's laboratory material. Here's the bones and figures locations in the text with the upper appendicular skeleton. This is always nice to have printed for yourself as you're going through the slides. Okay, the appendicular skeleton, the upper one. This is a page here of items that you're responsible for. We're going to do right now. And where did I get this? Right off of the website that I showed, Charlie's website. But this has in addition the figure location, figure number in your book where you can see this at the same time. So this is really a little bit more valuable to you. Helps move you through it. And obviously, if you look at the repeat figures, one figure being used for several things, you really don't have a lot of figures that you have to look at. Just showing you where that is. Okay, and then here's our material for today. That's followed by a practice quiz that only people who have done the first practice quiz should be taking. Everybody should be taking both of them. Okay, the upper appendicular skeleton. Well, what were we looking at before? We were looking at the axial skeleton, the skull and the spine. The axial skeleton had 80 bones. The appendicular skeleton, which is the arms, legs, pelvis. The appendicular skeleton has 126 bones. Now, we're going to do these rather, what will seem kind of fast. And you're wondering, how come we got 126 now, you saved, and we've only done 80? Well, the appendicular skeleton is perfectly symmetrical. And what you have in the right arm, you have in the left arm. So the bone you cover in the right arm or the right wrist is covered in the left wrist as well. So you really cut the number in down. Here's our first one. This is the scapula. If you're using that figure chart that I just showed you a moment ago, you can turn to the figure in your book. You don't need to, of course, it's right here. This is the anatomical view. The anatomical view means from the front, and we're not looking at this one from the back. Anatomical view. At the very bottom of the scapula, that point where you can reach back and it itches sometimes, that's the inferior angle. When you look at this, you do see a triangle. Up at the top, straight up, is the superior angle. This is a triangle with three borders. This side over here is the medial border. It's also called the vertebral border, and that would not be a wrong answer if you ever gave it to me. But it is more medial. Where's the spinal cord? Right here. Where's the spinal column? Right here. So this is the medial border. Across the top is the superior border. And then on the lateral side is the lateral border. That's also known as the axillary border, which is always the correct answer. But lateral border is easier for most people. Axillary border, they get that term from the axilla, which is your armpit. And your armpit is right here. This whole bone looks like a little scoop, a scoop, like for candy or for grain or anything. You'd hold it back here, and here's your scoop. And this area here is the subscapular fossa. Now, the subscapular fossa is the indentation, which I hope you can see in the image here, that would hold something. It even looks like an ashtray. If you remember, if you ever see, some people have never seen an ashtray. The word body refers to the subscapular fossa, the borders on all sides, and the angles, this whole thing. I won't be using the term lateral angle. There is a piece that comes out towards you. Remember, this is anatomical view. This is coming towards you. This is the coracoid process. It looks to me, you know, you have to pick a simile out for yourself. It looks to me like a broken little finger. It's the coracoid process. The clavicle sits on top of that. And then back or behind, we're going to see this in another view, is the acromion or acromion process. This is a large area of attachment for ligaments. So is the coracoid process. And so is this area here, which I'll name in a different slide in a moment, which holds the head of the humerus. Okay, now we're looking at both sides at once. On the left is what we just looked at. Acromion, coracoid process, superior border, superior angle, medial, inferior, lateral border. We're not going to do this. And subscapular fossa. Okay, so now let's turn it around, like this guy. Like you were going to slap somebody on the back. Okay, just at the shoulder. Here's the scapula. Here's our superior angle. Here's our inferior angle, not labeled because they're labeled right here. Here's the spine of the scapula. You don't feel your own scapular spines because there are muscles, big muscles here and in here, and that evens everything out. But here's the spine of the scapula, and at the end of the spine is the acromion, also known as the acromion process. Above the spine, there is a trough in which a muscle fits. This is the supraspinous fossa. And below the spine is the huge infraspinous fossa. What fits in these are the supraspinous muscle and the infraspinous muscle, which we won't get to until next week, or even the week after. Now we got one more view. We've got our first view, which is anterior. We just looked at the posterior view. And now we're looking at it from the lateral side. Okay, here's that coracoid process, that broken little finger I told you about. Here's the acromion process coming out towards you. This structure, though, flat, perfect size for your thumb, is the glenoid cavity. Some people call it the glenoid fossa. Again, we have to get used to the fact that in anatomy and exact science seems to have two names at least for everything. Okay, glenoid cavity. The head of the humerus, your upper arm bone, is going to fit into there. Now let's move back over here. We did the spine. We did the infraspinous fossa, supraspinous fossa. Yes, we did it all. We didn't go slow enough for you to memorize all of this, but to sort of get a snapshot. Here is a clavicle. Clavicle, collarbone, most frequently broken bone in the body. Okay. If you can envision this, one end is flat. This end up here, just look at the top one. This is flat, whereas the other end, I call it chubby. If you hold each end in your mental hand, hold with your left hand the flat end, that's the acromion or acromial end. Hold the chubby end. That's the sternal end. That's the end that fits in the clavicular notches of the sternum. And then one more guy right here, a bump. Turn it as in the lower one, and you have that bump. It's the conoid tubercle. The reason it's important, it makes contact with the acromion of the scapula. This is the acromial end here. When we say acromion, we mean of the scapula. Acromial end would be of the clavicle. I promise not to put together questions that would make you scratch your head. Take up your time thinking, what does he mean? What does he mean? I don't put questions together like that. Here's our humerus, the upper arm bone then. This is a posterior view on the right and an anterior view on the left. This is a right humerus. You'll see how I know that in just a second. The head of the humerus is rounded, and it looks like it has a skull cap. This is the anatomical view or forward view. Now you're looking at a person in anatomical view here. This is the front of their arm, their upper arm. This is where the arm attaches to the body. So the body must be over here. And this must be the person's right arm. Here's the head. Come across, there's a bump. This is called the greater tubercle. Turn it around, it's here. Greater tubercle. Come to the middle, and you have the lesser tubercle. Admittedly, they don't look too much different in size here, but they will in other bones that I show you. In between the greater tubercle, which is the most lateral one, and the lesser tubercle is a groove. This is the interturbicular groove. Interturbicular groove. It's just big enough to lie a pencil in, or to lay a pencil in. The surgical neck of this bone is roughly here. If you took your fingers like a pair of scissors, and if they were strong enough, you cut the bone right there. That's the surgical neck because that's where it usually breaks. The anatomical neck is higher. I'm not pleased with the description of anatomical neck here. This is the anatomical neck at the bottom of the cap. The line should be up there. Say shame on the person who put this picture together, and shame on me for not catching it earlier. The anatomical neck is here. Surgical neck is straight across here. Come down to the distal part of the bone. This is the proximal part where it's attached. We'll still take the anatomical view. Halfway down the bone, there's a bump. This is the deltoid tuberosity. This is one, even in class, people say, I can't see anything there. You can on this side. But people tell me I can't see it. Well, I say, close your eyes and feel for it. Then they can find it. You can always find it. It's a roughened surface. The deltoid tuberosity is for the attachment of the deltoid muscles. The deltoid muscles of the shoulder are up here. There are 3 parts to them, and they all come down and attach at the deltoid tuberosity. Come farther down. We get to the very end of the bone. If you could grab with your thumb and index finger the 2 sides of the bone here, the lateral side and the medial side. If you could hold with pressure just the bone with those 2 fingers, you're probably better than most of the people in the class, because it just rocks right out of it. It just pivots. But the side that is medial, and how do you know the medial side? It's the side the head's on. Has to be medial. This is a more pointed projection, and it's called the medial epicondyle. On yourself, put one arm out, not straight out, bend it, put your arm out, take your thumb on your other hand and feel your inside elbow and find a bony projection. Pretty close to what we call the funny bone. That's the medial epicondyle, needed for the attachment of muscles. Here it is on this side. I don't know if you've got short sleeves on, and this is hard to do on yourself anyway without a mirror, but we'll get somebody to demonstrate it when we have all the pictures of people up here. But if you now tap your elbow on the lateral side with your other hand, find the bump, the bone. You've seen it before. Sometimes it seems like it's there, and other times you hold your hand just right, it's there. That's the lateral epicondyle. And then if you take one arm out, bent, then your other arm, middle finger and thumb, and put it under the elbow of the other arm. Find and touch at the same time lateral and medial condyles. They probably feel quite a bit farther apart than this picture makes it look, but that's because you have a lot of connective tissue and muscle attached to these guys. Lateral epicondyle, medial epicondyle. This coloring here is primarily so that you're brought into focus on something. It really does not exist, the coloring. I want you to find a ball in our diagram. That ball is called the capitulum. Capit means head. So anytime you get something round or skull shaped, they like to use the word capit. So this is the capitulum here. The radius, no, I got fooled by their drawing too. Okay. Okay. Here's the capitulum, I'm sorry. The capitulum is on the lateral side, and it attaches below it to the radius. We'll see the radius in a moment. The radius is always on the lateral side. The radius is always on the thumb side. The thumb is always on the lateral side. This structure they're showing here is the trochlea. Now, their drawing again overlaps. It almost makes you think that which is that? The trochlea would end here. The ulna, the other bone of the forearm, when you flex it, bring it up, bend it up, tighten it up, it rotates over here. A piece of it goes into this cavity called the coronoid fossa. When you move the radius up, it goes into the radial fossa, not shown here. When I say not shown here, it doesn't mean I'm not going to show it to you. I'll show it to you well, or you'll never get quizzed on it. Okay. Radial fossa makes sense to me. The radius goes into this cavity, the bottom part. The coronoid fossa, why don't they call it the ulnar fossa? Would have been much easier for us, but they didn't. So the coronoid fossa versus the radial fossa. Coronoid fossa is towards the heart. Coronoid towards the heart. Sort of the trick we had to play with the coronoid process of the mandible. Turn this around. They're showing that the trochlea can be viewed from the posterior, but there's a large cavity. This is the olecranon fossa. The olecranon is a structure on the ulna that is, I'm sure, in the next slide, and fits into it. Let's get to the next slide to clear things up. Oh. This was a little mini quiz I put together. What do you think that's pointing to?
The head.
The head. That's correct. Okay, now, if that's the head, come across to this side versus this one. I want this one first.
The intertubercular groove.
No, but it's close. Here's the intertrabecular groove right here. This is
Greater
the,
tubercle?
what?
The greater tubercle?
Thank you, that's it. What's this one then?
The lesser?
Tubercle. Correct. Okay. Here, I'm going to answer this one. This is the anatomical neck going around the head. And down here farther, the surgical neck. Okay, looking at your notes if you have them or anything, what do you think that is? Halfway down the humerus.
the deltoid tuberosity.
Exactly. Thank you. Okay, now we've got a few more down here. This is nice. Okay, now this is still a right bone. Here's the rounded structure down at the very distal end. Anybody want to give a try, please?
Capitulum.
Capitulum. And the radius rotates up into this slot here, the radial fossa. This is the trochlea, and above it, the coronoid fossa. This structure here
Medial epicondyle.
Oh, sorry.
Say it. No, somebody was trying, thank you, but I didn't catch it.
Epicondyle, medial.
It is the medial epicondyle. Okay, epicondyle means a bump on top of a bump. Okay, epicondyle. Okay, that was good. Good because you recognized it as medial. Where's the lateral epicondyle? It's not labeled here because it's so small in this picture. Oh, well, not everything is on this one, but it is your answers. Greater tubercle, lesser tubercle, head, intertrabecular sulcus. Now the surgical and anatomical neck are not here. It's the same picture. Deltoid tuberosity, coronoid fossa, medial epicondyle, trochlea, capitulum, and the radial fossa. For those of you who play chess or ever saw a chessboard and know what a pawn looks like, turn this upright. There's the head of the pawn. There's the base of the pawn. This is the ulna, one of the two bones of the forearm. Some people think it looks like a carnivorous plant. Others think it looks like a wrench. Others think it looks like a snake. I don't care what you think it looks like. Pick the one that helps you the best. This curved portion, and this is upright now, okay? So the most proximal part is up here, and the most distal part is down here. This is facing you, and this is a profile, okay, on the right side. This is the trochlear notch, also known as the semilunar notch. I'm not coming into focus very well here, but it's good enough. This fits into the intercondylar fossa on the back and rotates up the front when you flex your arm. Here it is over here, trochlear notch. The top part is called the acromion, olecranon, or olecranon process. That's this. Come all the way down the trochlear notch to the very end. The jumping off point, that's the coronoid process. Here it is over here. When you're looking at an x-ray of the elbow, it can be quite confusing until you find the coronoid process, and then everything falls into place. This is the coronoid process. This is what goes into the coronoid fossa. when you rotate your hand upward. In other words, you flex your lower arm. Turning it sideways, turning it sideways, we see a marking. We can feel it too when we have the actual bones. This is the radial notch. The head of the radius is going to occupy that spot. We'll see the radius in just a second. At the distal end, on each one of these is a styloid process. Here and here. This was not labeled. Styloid means pen-like or quill-like. Styloid process. You do not have to know the head of the ulna, but it does serve here to point out that the head is not always the biggest part. Okay. Here's the radius. Here's the radius head. That's what fits right there. Head, neck, radial tuberosity. When we did the rib the other day, it was head, neck, tubercle. But the tuberosity is bigger, and for the radius, it's head, neck, tuberosity. You need to keep those two clear. Head, neck, tubercle in the rib, head, neck, tuberosity in the radius, or you'll miss a question. Don't need to do that. Come down farther. Here's the ulnar notch. The notch means that's where the ulna is going to touch at the distal end of the radius. And then at the distal end of the radius is the styloid process again. So the radius and ulna both have styloid processes. If you stand these upright, touch them to a table top, stand them up on a table, the only thing that will touch is the styloid process. And now the hand. People used to think that the hand was the hardest thing. I cringed at it myself, not for me, but trying to get it across to people. The hand is not that hard. We can break the hand down very quickly and use your books and figures to help out. First off, let's start with the fingers. The fingers start here where the arrow is and move up. There's 3 bones, 3 bones, 3 bones, 3 bones. And then for the thumb, there are only 2 bones. All of these bones individually are called a phalanx. The plural, there's phalanx here. The plural is phalanges. And this is easy, watch. This is the distal phalanx, farthest away, the middle phalanx, and the proximal phalanx. In naming these bones, however, a specific one may be picked out, like this one I'm touching right now. This bone is the proximal phalanx of digit 4. Here are the numbers for the digits. Your thumb is always digit 1. Your big toe, when we get to it next time, is digit 1. For the first digit, the thumb, we only have 2 bones, the proximal phalanx and the distal phalanx. There is no middle phalanx for the thumb. Okay, you can pick out any. Middle phalanx, digit 3. Distal phalanx, digit 5. the little finger. So how many bones did we have here in front of us that are phalanges? 1, 2, and then 3 times 4 is 12, and the 2 is 14. And there's 14 more on the other hand. So we just covered 28 bones. Just covered 28 bones. Now go to, away from the fingers, so go to the palm of the hand. And the palm of the hand has 5 bones, numbered 1, 2, 3, 4, 5. Well, you can't give that as an answer. Bone 1 is metacarpal 1. Bone 2 is metacarpal 2. Metacarpal 3. Metacarpal 4. Metacarpal 5. And here's the word metacarpal for you. Okay. Remember, thumb is always number 1, little finger is always number 5. 1, 2, 3, 4, 5 for the metacarpals. 2 hands have them. So there's 5 on each hand. We just covered 10 more bones. I always like this part. And who said the hand was hard? Well, now this is why they say it's hard. Because you got this mess of bones down here. There are 8 bones left. And they make up your wrist. And they're called carpals. Carpals. Here's how you can do these. I'll show you on 2 different ways. Start at metacarpal 1. Come down, and the single bone that it touches is the trapezium. Yeah, now you have to memorize a word here instead of a number. Trapezium. Metacarpal 2 comes down and touches this one bone. You know, it has dominion, let's call it, over this bone. The other ones want to crush in, but this is the trapezoid. The trapezoid. Trapezium, trapezoid. Metacarpal 3 is the easiest, I think. Comes down, it articulates with one bone, the capitate. Some people think that looks like a face. Okay, they got good imaginations, but it works. Metacarpals 4 and 5 together share this bone here. And this is the hamate. How many bones did we just do? 4. We did the trapezium, trapezoid, capitate, and hamate. These 4 carpals are the only carpals that touch the metacarpals. The remaining 4 that we're going to do not touch the metacarpals, which separates them. If we come on over to the trapezoid, a trapezium again and trapezoid both, these 2, go under it, there's a large boat called the scaphoid. It's also known as the navicular. Scaphoid, the more common name these days. Follow it along. The next bone it touches is the lunate. It's going underneath the capitate here, but this is the lunate. The next bone that is touched still has a lot of names. It's the triquetral, meaning triangular. Triangular is the second name. Triquetral, triangular, and triquetrum. Well, I'm not going to fool you with any of this. I'll probably pick triangular. There's one more bone because we've only got 1, 2, 3. We need 4 plus 3. We need one more because there's 8 carpals in each hand. and it's barely showing here. It's called the pisiform. I'll show it to you better in the next picture. Okay, bones of the hand, thumbs over here this time. So metacarpal 1, 2, 3, 4, 5. Come down metacarpal 1 to the trapezium. Metacarpal 2 to the trapezoid. Metacarpal 3 to the capitate. Metacarpals 4 and 5 to the hamate. Underneath the trapezium is the scaphoid, coming around here. Next is the lunate. The next is the triangular. And the last one, a P-shaped little bone called pisiform, which means P-shaped little bone. This is a nice picture, so that you can check yourself. I'm not privy to what the 2s and 3s stand for on this one. And they are calling T1 triquetral here, but you understand it's also triangular triquetrum. Okay. The rest are all the modern day names. Okay. Does that look hard? Or does it just look like work that has to be done?
I think it doesn't look too hard. Just like you said, a lot of work has to be done. Makes sense.
Yeah. It's, there's a lot of jobs that any of us probably couldn't do, but there's a lot of jobs that we may not want to do, but we could do. On the other hand, knowing what your career goals are, hopefully you're in an even better spot than that. May not be automatic that you learn this, but you want to learn it. You'll have use for it. Now, eventually we are, after we finish the next set of bones, we're going to be looking at x-rays, because when you get on the job, assuming you're in the health field, you are going to be looking at x-rays, aren't you? Or you think you're going to look at bones? You're not going to have a bone box next to you trying to match up the patient's with the patient's x-ray. You have to know the x-ray. But and there will be a modest for sure, number of questions on the practicum that use x-rays. Nothing to be worried about at all. X-rays are pretty darn straightforward once you know how to read one, and we'll show you that. It's not going to be difficult. But the x-rays are what you're going to look at in real life, unless it's a compound fracture, then you'll at least see a bone. Okay. Okay, it's 4:01 right now. And what I'm going to ask you to do is I'm going to end our session for everybody, and then take a 10-minute break to 4:10. And for those of you who want to come into the discussion area, please join the discussion class. Log in the same way as always, but go to the other class, and it'll be set up for you. It's set up right now. You can actually get into it right now. I set it up for 4 o'clock, but I want to be able to give everybody a 10-minute break. Attendance at the discussion section, it's meant to help you. If you don't feel you need help on this topic, you really don't need help on this topic at all, or review, I'm not going to take attendance. attendance is taken automatically anyway by Canvas. I am not grading on your attendance here. Okay, I'm putting this out for you. You spent your money, and I want you to give it a try. Okay. So, any last questions for the whole group here?
I have a question.
Yeah.
So the library closes at 5. So is it okay if I join the discussion but have my camera off because I'm going to be driving?
Oh, as I said, I'm not going to be grading on the discussion on anything other. Well, when you get there, I'll explain it. There's one little thing, but mainly the chapter outlines. If your camera's off or whatever, that's okay. Okay.
Okay. And then last question, the bone that sticks out like on your ulna, is that the styloid process, or would that be the like right here, like the the little bone that sticks out?
At the bottom, at the distal end.
Yeah.
Yeah, styloid process
It's a styloid process. Okay.
of the ulna. Okay. Okay. So some or most of you I'll see in just a few minutes. Take 10 minutes. It's now 4:03. Let's call it 4:05. Let's call it 4:15. I'm going to go ahead and end this now. Otherwise, I can't get into the other one.